There's an interesting feature of how this power supply is built that I would like to point out. For the 723, the chip needs to be powered clearly by voltage that's higher than the output and higher than what's fed for the transistor, or at least this node here, because we need to drive the base of this transistor. It's a Darlington pair it's set up as. If you look at it, full rated current for this power supply is 5 amps. That 5 amps is going through Q102. This is a big current. Big current, we have a voltage across here. This needs to be at least a few volts. If it's a few volts at 5 amps, now we're talking 10 watts. 10 watts of power. That's why Q102 is a large transistor and it's bolted to a big heatsink. What we don't want is don't want V raw to be a very large voltage here, because that just makes more power dissipation here and it makes our power supply less efficient. Now, a linear power supply is not particularly efficient in the first place, but we should at least not shoot ourselves in the foot. Problem is that we need, like I said, for this chip, for the output of here, to be able to drive higher than the 5 volts, but not have the collector voltage to also be too high. We can get around this by powering the chip by a higher power supply than V raw, than this one right here. We can do that. If we can do that, that higher power supply is much lower current because it's just powering this. It's nowhere near 5 amps, just a few milliamps. So just very low power supply, which means we have very little constraint on how we can do that. No heat sinks involved. So we look at this, it's the same figure. We have V raw here. Check out this. We have this this wire coming off of here, comes over here. It's another transformer winding. Follow the other side of the transformer. This secondary goes through a diode here. We've got a capacitor. Remember that this node and this node and this node, they're all labeled as minus. They are actually all the same node and connected together. So if you draw them connected together, it's better to see. But this half-wave rectifier totally looks like a half-wave rectifier. Transformer, diode, capacitor, positive half-wave rectifier. You would expect it to be drawn like this. Okay? And indeed it kind of is, but that's not how this is drawn. You would expect this to be like the 0 and here's the output. How this one works is we have the transformer windings. Okay, we have our full wave rectifier. We have our capacitor. But this capacitor, I'm going to draw it this way. It goes all the way down to 0. Alright, but 0 is not where the other side of the secondary is attached to. It's actually attached to V raw. So it's attached on top. What I'm going to do is I'm going to draw V raw as a voltage source, which takes into account this winding of the transformer and the bridge rectifier, everything required to get us to between here and here, these capacitors C101 and 102 to get V raw. If we look at this waveform goes up and down, but if we just kind of call out what's going on at this node, right, plus minus here, looks like this. Here's V raw. That waveform is not centered around 0, it's centered around V raw. So it goes up, and down. It's just shifted up by V raw. And then the half-wave rectifier is going to use a different color here, come up, and then discharge, come up, discharge, and now we have a power supply that is higher than V raw. This doesn't notate what the winding voltage is or what the turns ratio or anything is, but we do know that we're going to get a power supply that's higher than V raw. It's filtered by capacitor 103, 100 microfarads, and the milliamps that's drawn by this is very little ripple. There's no regulator here, but the ripple is going to be fairly small. Current drawn out of this is small. So that's a neat way that we can get really low, cheap, low current power supply, one capacitor, one diode. The only difficulty with this is we do need another winding for the transformer. So whether you call that cheap or not, it kind of depends on your situation.